Welcome to Physics with Joe. In my last video, I talked all about free fall. Free fall generally is referred to one-dimensional motion vertically, where an object is dropped, thrown straight up, thrown straight down, where gravity is the only force acting on the object. There's no air resistance, there's no other forces but gravity, and if that's the case, then near the Earth's surface, all objects will accelerate at negative 9.8 meters per second squared, regardless of their mass or size. Today I'm going to talk about projectile motion, which is very similar to free fall, except instead of just having an object traveling vertically in one dimension, now we're going to look at objects which are launched at an angle. So that means it's going to be traveling both vertically and horizontally at the same time. So without further ado, let's launch right into it. Before I launch right into discussing projectile motion, let me show you a great applet that'll help demonstrate some of the key components, pun intended, of projectile motion. In this applet, I have a pumpkin which is being launched from on top of a 12-meter platform. The initial speed is 20 meters per second and the initial angle is 55 degrees. What we're going to look at as this pumpkin is moving through the air is the velocity vector. So what you'll see are three different arrows. The big green arrow represents the velocity vector, and the length of the arrow is going to be proportional to the speed, and the arrow is going to point in the direction the projectile is moving. In this case it's a pumpkin, but it doesn't matter if there is no air resistance. So the longer the arrow, the greater the speed. The shorter the arrow, the smaller the speed. Also shown are the x and y components of the velocity vector. The x component is how much of the velocity vector points in the x direction, so how fast this projectile is moving horizontally. The y component is how much of the velocity vector points in the vertical direction, so it's how fast this projectile is moving vertically. So look at the lengths of the arrows as this pumpkin is moving through the air and see what you notice. Hey, let's do that one more time. As you watch that applet of the pumpkin being launched through the air, what I hope you noticed was that even though the velocity of the object was changing the entire time, so the speed was changing and the direction was changing, it was actually only one component of the velocity vector that was changing. What I hope you saw was that the horizontal component of the velocity, how fast the object was moving horizontally, did not change the entire time the object was in the air. It was only the vertical component of the velocity. So what that means is, anytime you launch an object, whatever its initial velocity is in the x direction, it will have that horizontal velocity the entire time it's in the air, which means ax, the acceleration in the x direction, is 0. On the other hand, it was only the vertical component of the velocity that was changing, and as we saw in free fall, the acceleration in the y direction is negative 9.8 meters per second squared, or 9.8 meters per second squared straight down. So as an object is moving through the air, the vertical component of the velocity is constantly changing at a rate of negative 9 meters per second every single second, which means the acceleration in the y direction, negative 9.8 meters per second squared. So if I had to sum up projectile motion in just two statements, it would be projectile motion is horizontal motion with constant velocity and vertical motion with constant acceleration. The other important point about projectile motion is the horizontal and vertical motions are completely separate and they do not affect each other. So the horizontal motion does not affect the vertical motion and the vertical motion does not affect the horizontal motion. Classic example is, let's say I dropped an object and fired an object horizontally at the same time, which would hit the ground first? And although it may be counterintuitive, the answer is both objects will hit the ground at exactly the same time, because if I drop an object, it has no initial velocity in the y direction. If I launch an object horizontally, it also has no initial velocity in the y direction. So the y components of motion for each of these objects are exactly the same. Let's take a quick look at that using another applet. This applet is going to show a race between an object which is dropped straight down versus an object which is launched horizontally at the same height as the first object, and see which one will hit the ground first if there is no air resistance. Well, let's first look at the motion of each ball individually. The red ball is going to represent an object which is just dropped straight down. If I play it, you'll see that as the object is moving downwards, the distance between the dots is increasing, which is showing that the object is increasing in speed and covering more and more ground every second. So now, though, what happens if instead of just dropping it, I launch it horizontally? So the ball still has no initial velocity in the y direction, but it's moving horizontally. Well, that is going to be represented by the blue ball. So if I launch this horizontally, you'll see the blue ball moves in a parabolic trajectory. But if I separate the x and y components of the object's movement and look at them individually, what I'll see is that this parabolic trajectory of the blue ball is really a combination of horizontal motion at a constant velocity, so it's moving at the same velocity horizontally the entire time, vertical motion at a constant acceleration. It's behaving just exactly the same as if it was dropped from rest, because the initial velocity in the y direction was 0. So now if I look at both, what I see is that these two balls will hit the ground at exactly the same time, because they were both released from the exact same height. They both had 0 initial velocity in the y direction. The only difference was the blue ball had an initial velocity in the x direction, whereas the red ball did not. Now that we know that projectile motion is really a combination of horizontal motion at a constant velocity, so ax equals 0, and vertical motion at a constant acceleration of ay equals negative 9.8 meters per second squared, and we know that we can treat the vertical and horizontal motion separately, let's finally take a look at the equations of projectile motion. Well, the equations in the vertical direction are exactly the same as the equations of free fall. There is no difference. So our four big equations, we have Vy equals V naught y plus Ay delta t, y minus y naught equals V naught y delta t plus 1/2 Ay delta t squared, Vy squared equals V naught y squared plus 2Ay y minus y naught, and y minus y naught equals 1/2 V naught y plus Vy times delta t. Those all still apply, and we know that near the Earth's surface, if there is no air resistance, the acceleration is Ay equals negative 9.8 meters per second squared. Now, in terms of the horizontal motion, we still have the four equations of constant acceleration that we can apply in the horizontal direction, but since Ax equals 0, what we're going to see is that these four equations actually reduce to 2. And in fact, one of them is just not even a real equation. I don't mean to insult it, but it's kind of a quasi-equation. So in the horizontal direction, we kind of have one big equation that we'll use. Well, the four equations of constant acceleration in the horizontal direction, we have Vx equals V naught x plus Ax delta t, x minus x naught equals V naught x delta t plus 1/2 Ax delta t squared. We have Vx squared equals V naught x squared plus 2Ax, x minus x naught, and last but not least, x minus x naught equals 1/2 V naught x plus Vx times delta t. Well, let's take these equations and plug in the fact that we know the acceleration in the x direction is 0 meters per second squared, and see how they simplify. Well, that first equation, Vx equals V naught x plus Ax times delta t. If I put in that acceleration in the x direction is 0, what I get is Vx equals V naught x. So the velocity in the x direction does not change the entire time the object is in the air, and gravity is the only force acting on it. Second equation, x minus x naught equals V naught x delta t times 1/2 Ax times delta t squared. If I plug in Ax equals 0, what I get, x minus x naught equals V naught x times delta t. In sort of my view, this is the only real equation we have when dealing with the horizontal motion. As long as we realize that the velocity in the x direction never changes, the only equation we have to work with positions and velocity and time is x minus x naught equals V naught x times delta t. Well, if I look at these last two equations, Vx squared equals V naught x squared plus 2ax x minus x naught. If I plug in acceleration equals 0, I get Vx squared equals V naught x squared, or Vx equals V naught x, the exact same as what the first equation reduced to. And then last but not least, we have x minus x naught equals 1/2 V naught x plus Vx times delta t. Keeping in mind that Vx does equal V naught x, I can plug in for Vx V naught x, and what I get is x minus x naught equals V naught x times delta t, exactly the same as what the second equation reduced to. So in projectile motion, in the horizontal direction, we know that Vx equals V naught x, velocity in the x direction doesn't change, and the only real equation we have to work with is really just x minus x naught equals V naught x times delta t. The very last thing you need to know before you can start solving problems is, how do I get the initial velocity in the x and y direction? And the answer is very simple, just like calculating the components of any vector. If I'm given the magnitude, which is just going to be the initial speed, and I know the launch angle, which is going to be given with respect to the horizontal or respect to the positive x-axis, then what you'll see is that the x component of the velocity, V naught x, this is just the adjacent side, and it's going to end up being V naught times cosine of the launch angle. So the initial velocity in the x direction is the initial speed, V naught, times the cosine of the angle. The y component of the initial velocity, you'll see this is the opposite side to my launch angle. So the y component of the initial velocity ends up being equal to V naught, the initial speed, times the sine of the launch angle. Well, that is really it for the introduction to projectile motion. We now know that projectile motion is just two-dimensional motion without air resistance, where gravity is the only force acting on an object. And in projectile motion, an object moves horizontally at a constant velocity, vertically at a constant acceleration, and I can treat the horizontal and the vertical motion separately because they're independent of each other. We also know how to calculate the x and y components of the initial velocity. V naught x is just V naught times cosine theta. V naught y is just V naught times sine theta. That's really it for my introduction to projectile motion. In my next video, I will do a detailed example problem looking at many different aspects of projectile motion and the different kinds of quantities that you can calculate. So until then,